Hi, guys, and welcome back to another episode of Women in Math and STEM, where our mission is to reach out to as many professionals, aspiring professionals, students, whatever you name it. We try to reach out to them, who essentially support the initiative of bringing more women and young girls into the STEM field. So, with that being said, as always, feel free to open up the description or transcript to better follow along, and I hope you enjoyed this episode. Hello, and thank you so much for coming to this call and talking to me. Just to sort of start off, do you mind walking us through your math journey to get you where you are today?
Yeah, so I actually knew I wanted to do math pretty early on in grade school. I went to school in Bosnia, which then was even a different country called Yugoslavia, and we had the system where you selected a kind of an elective in fifth grade, and I chose math. Then I went to high school that was specifically for math. We high schools when I was growing up were specialized like this according to subject. So I went to like a math, physics, CS high school, and then I came to the U.S. to do my senior year of high school. And I already knew at that point I wanted to do math. So I graduated high school, enrolled in college, majored in math, did my PhD in math, became a math professor, everything math. The reason I sort of knew this so early on that math was my thing is I just kind of liked how math could do two things, right? That seem like they don't go with each other, but they actually do. So one is that math explains the world, right? It can give us insight into how the universe works, right? But at the same time, it's really abstract. Like you can do abstract math without any connection to reality, right? It's like this philosophical exercise that you're doing. These rules of logic. It's like a game. You have these rules of logic, and then you're applying them to develop mathematics and sort of work within the world of mathematics itself. So I thought that was like the coolest thing that you can do both. That this thing can do both. So that's why I like math. That's a long answer to your question.
That makes sense. I was just wondering, since you recently published a book called, like, as you can see in the background, Making Democracy Count, I was wondering, like, what was the inspiration or, like, motivation to applying math to, like, politics and voting?
Yeah, so my wife thinks it's pretty cringy that I put the book cover here. I just did it the other day, but I don't know. I'm experimenting. What do you think? Does it work? Is it okay? It's not obnoxious. Okay, good. So uh yeah, so my interest in this interdisciplinary field that combines math and democracy dates way back, actually, to that time when I came to the U.S. Uh, I came to the U.S. because there was a war in my country, so I was a refugee here, and it always bothered me. Well, there were these two elections that took place back home in the early '90s that sort of that led to a war, right? And I always wondered, what if we used a different election mechanism? Because I knew enough math to realize that there was some kind of math happening behind the election process. Namely, you have to add up the votes somehow, right? That's math. So how are you adding up these votes? What is the method, the process that's actually tallying the votes? And I knew there were different ones, right? So what if in those elections different methods were used? Maybe some of this, you know, uh, what followed was a complete breakdown of democracy, right? War is about as far as you can get from functioning democracy. So I wondered, could some of this been avoided if a different system was used? Maybe that system would have taken in or would have understood the will of the people better somehow, because it was somehow more wholesome or something. I don't know. I had these like vague notions at age 17 that math mattered in this process. All right. So fast forward 20 years or something, and 2016 elections happened, where you have the situation where Hillary Clinton had more votes, 3 million more votes than Donald Trump. But Donald Trump won because of the electoral college system. Okay. So there's math behind that. How can you have this discrepancy? What is the electoral college? How do you tally it? Where does it come from? What's the, it's tied, electoral college is tied to the number of seats, of number of representatives each state gets. So how is this done? What's the mathematics behind allocating, dividing the House seats to states, allocating states to states. So quickly I realized there's really a lot of math that very few people are paying attention to, math that's not being questioned. We're not really wondering, are we using the best math for these processes like tallying votes, allocating, legislative seats, etc. And I decided to sort of use my expertise as a mathematician for this. So that's how I got into the whole business of math and democracy. I started teaching a class at Wellesley College where I work called Math and Politics. Today is the first years are arriving on campus last week, and today they're registering for classes. And I have like 40 emails sitting in my inbox right there on the second screen saying, oh, I couldn't get into your math and politics class. Please, can I get in? I'm on the wait list. Is there anything I can do to get in? So it's a popular class precisely because it combines these two cool things, politics and math, in an unusual way. I feel like my answers are going to be long-winded for earlier questions. So feel free to stop me and cut me off anytime you want.
No, I think your answers are good. I was just wondering, sort of on the same note, how like you sort of discovered that mathematics like exactly improves our current system, or like how the changes may be like better or different.
Yeah, so once I started digging and trying to understand how things actually worked, I realized, wait a minute, this math is horrendous. For example, the way we vote, right, in most elections. Let me back up. There are 520,000 elected officials in the United States, okay? And almost all of them are elected using plurality voting or first past the post, winner take all. This thing has many names. So what is it? It's the simplest, dumbest thing you can think of. You go into the voting booth, there's a bunch of candidates, you circle one name, and that's it, you walk out, right? The candidate then, with the most number of votes, wins, okay? But the problem is, most doesn't necessarily mean majority, right? If you have 5 candidates, you could win with fewer than 50% of the votes, right? People could have like 20, 30, 35, 20, right? So you could win with 20, 30% of the vote. And this happens a lot. So what you're seeing is that people who are first choice for a minority of voters actually get to govern 100% of the voters, right? So somehow this process didn't really capture the feeling of the majority, or didn't capture the consensus in the population. So you have all kinds of mathematical consequences of this fact. You have things called vote splitting and the spoiler effect and the Duverger law and center squeeze effect. I mean, books have been written on the mathematical consequences of this method of voting. The essential problem being is that it's too simple. The math is too simple. We're making it too simple. Yes, it's easy for people just go in there, circle one, vote, but math can't do very much with this. And that makes this process problematic and unrepresentative of what's really going on in the minds and hearts of the voters. Right. So similarly, lots of other processes run according to some either math that's too simple or that's too old, archaic, like maybe it worked at a certain time in history, but it doesn't, or we blindly copied it from somewhere else and we're just using it. Most of it forgotten, most of it unquestioned. So once I realized this, I was like, wait a minute, we need to update this math, change it or update it or something, because it's causing our democracy to function in a very, very poor, unrepresentative way.
I see. I think you mentioned that the math we use right now is like too simple almost, and it should be like more complicated to be more representative. I was just wondering how you go about sort of explaining this complicated math to like other people who may not have like a mathematics background, to sort of get them to sort of buy in on the idea.
Right. So that's a very good question, and luckily you can explain this math at various levels. So I'll stick with the voting example. So if you trust me, then plurality voting is bad. Okay. So circling your top choice is not sufficient. All right. It gives you some information, but not the full picture. Well, how can you gather more information? So you can ask the voters to not only give you the first choice, but maybe also their second and third and fourth, etc. Ask the voter to rank the candidates in order of preference. Okay. Now, what does that do? Well, you collected more information from the voters. That means that you can actually do more. Math can do more with this, right? And now there are tallying methods that take all this information in, right? There's math, this is called ranked choice voting, that can sort of soak in all this information and give you a winner that really is it better represents the will of the people because people told you more about their will, right? Now, you can explain this to the voter without getting into the math of how this actually works. There's like this iterative kind of elimination and retabulation process, and until somebody reaches the threshold of 50%, and if I sat down with you for 10 minutes with a pencil and paper, I could explain it to you and you'd be happy with it. You'd say, yeah, this totally makes sense. Why aren't we doing this, right? But people who are afraid of math, and most people are, you just don't get into it. You try to convince them that it's better if they give you more information, and the math will do the job. However the math works, it'll happen. Just sort of trust me, right? Trust me, I'm a doctor. Type thing. And most people actually trust this reasoning. It's been shown that if you can reach people and educate them about things like ranked choice voting, they are very responsive to this. It just makes sense. Like, give me more information so I can give you a better result. That's it. People respond to this very nicely. There are other things that are a little more complicated, and you sort of can't sort of water it down so much. You have to get into the math of it a little bit. One example is gerrymandering, right? So gerrymandering is this process of sort of drawing district lines so that the outcomes are kind of predetermined. There's a preordained winner according to how you kind of carved up the district. Now, the reason why that's complicated is because, well, it's complicated. There are rules about how you may or may not draw district lines. There's geography to contend with, right? If you have a river, that's going to impose some kind of a border, right? You have demographic data. You have to follow things like the Voting Rights Act, where you have to give minority populations representation. You have to deal with things like respecting county boundaries, city boundaries, et cetera. So you have to work those into the district. So there's a lot of parameters that come into the question of districting, and consequently, the question of detecting malicious districting, namely gerrymandering. So the math just has to be more complicated because there's so many parameters. There's no way you can have like a simple, solution to this problem, right? So it's a little harder to approach the public and say, look, this is what we should do. But mathematicians, we're trying. We're learning how to be better communicators about this thing. What's important is that there's trust in what we do, right? And I think there still is. A mathematician typically is someone who is really, mathematics is so objective and universal and formal and nonpartisan and apolitical that, if you were to think of a profile of a person who is as detached from politics as possible, it would be like a crazy mathematician sitting in her office, right, proving theorems. So I think there's a good moment here where we are doing some work. We are sort of doing a lot of outreach and research, and getting out into the real world and saying, look, this is just math. It's not Democrats and Republicans. It's not. It really has nothing to do with politics. Like, math says we can do better, and I think we have some momentum here that I hope we can capitalize on in the coming years.
And then, sort of based on your experience, where do you really see this field or like the voting system in like a couple years or like a decade from now?
I think it's just going to blow up. I think there's very exciting stuff happening here, and I'll tell you why. Because we are learning to be more interdisciplinary now. Interdisciplinarity and transdisciplinarity is all the rage on college campuses now. And I'm glad it is so, because life is interdisciplinary. Life doesn't come to you in these compartmentalized units, like where you study about this aspect of it in the physics department and that aspect of it in poli-sci department, etc. Right? We are coming together as in the scholarly world and learning how to talk to each other, how to share information, and how to adapt to different points of view, etc. Right? So this is happening. This is precisely where this quantitative political. So there's, I think there's names. So like computational social science is one of the emerging fields of study. Well, it's a field that, like the name tells you, you have some kind of a social science, like political science or something like that, that's not necessarily known for its quantitative aspects. It's not mathematical, right, in its nature. But the computational part is now coming in. So data scientists, mathematicians, statisticians are bringing their expertise into social science. We're meeting social scientists halfway and producing these new points of view that are quantitative, mathematical in nature on problems that they have been contending with for decades, right? So there's a lot of exciting stuff happening in these intersections of fields. And that's why I think this is just going to blow up, because now is the moment where, like, people are realizing, wait a minute, we can actually tackle these social science issues or in the humanities also. We can tackle all these questions quantitatively, mathematically. We have access to a lot of data, like data clouds are just like flying all around us all the time. And we have greater computing power where we can actually handle this data and extract some useful information from it. So short answer is, I think there's sort of exciting times are ahead of us.
That sounds great. I was also just curious about, were there any like research projects you did or sort of work you've done that have yielded really surprising results or something that's really shocking?
I don't know about shocking, but there have been some cool. So my field of study is called topology. Now, topology is like a cousin of geometry, where you study spaces, like geometric spaces, but you're allowed to squish them and deform them, right? So technically, you study kind of geometric objects up to continuous deformation. That's like a technical term. So what does that mean? So if you take in geometry, if you take a circle and a square, those are two different objects, okay? But in topology, they're not. To me, they're exactly the same thing, because I think of like a square made out of string, and then I just like smooth out the edges and the corners, and I turn it into a circle. And that's continuous deformation, namely nothing violent is happening. I'm not cutting or poking holes or anything like that. So from the point of view of topology, those are two exactly the same objects, right? And this makes sense, because you want to study things like this, because lots of things change shape, but they're the same. Like, think of a tree swaying in the wind. It's still the same tree, even though it's moving. The universe is, expanding or shrinking. I forget which now. it does a different thing every day, it seems. But it's still the universe, right? If you have a soccer ball and you sit on it, well, it's not that round anymore, but it's still a soccer ball, just squished it temporarily, right? So it makes sense that there's a field of study that does geometry, but in its kind of, it allows for this deformation. So I have been able to bring certain aspects of topology into the study of political structures, right? And that's been very cool. These two things seemingly have nothing to do with each other, but it turns out you can model certain power structures and the formations of coalitions in a political system and kind of the power dynamics in political system. You can model it using certain topological tools. So that's been very, very exciting and cool to me. And I've had lots of students work on this stuff, and it's an excuse to learn a lot of cool math, namely topology, and to learn how modeling some of this intersection of social science and computational stuff comes into play. So again, shorter answer, nothing shocking or super surprising, but I feel good about having married kind of two fields that at first glance look totally different.
And I think speaking about like blending the two fields, I was just wondering, since you said your class was so popular, what exactly like do you do or do you think like makes the class or just sort of like this intersection of two seemingly like unrelated fields so popular?
I think you said it. It's the intersection of this seemingly unrelated fields. People are intrigued. The title of the class is Math and Politics. They're like, what does that have to, what does math have anything to do with politics? So they're intrigued. And I teach at a place where students are very ambitious and interested. And when their interests are peaked like this, they act on it, right? They like to be challenged. They like to see new things and hearing things. So they come to this class, and then we start talking about voting methods, apportionment of legislative seat, electoral college, districting, gerrymandering, quantification of power. That's a big subject in what we do in the class. And the math is not too hard. All you need is basic algebra. And so it's not scary for people, right? There's no like calculus or anything that I throw at them. Plus, there's all this stuff we bring in from political science, economics, history, even psychology. So the students really respond very, very well to that. And I love having, so what happens in this class is I get students from all across campus, from all kinds of majors and departments. So I have students who are majoring in, math and statistics and data science, but also history, political science, peace and justice studies. What else? What am I missing? Yeah, poli-sci. I had like 13 majors last year when I was teaching. Out of 24 students, they came from 13 different majors. Yeah, so from all of psychology, I mean, there was like a French major in there, all over campus. Just because it just sounds interesting, and there's the word out on campus now. I've taught it a bunch of times now that it's fun in this kind of interdisciplinary way.
Sounds good. I was also just wondering, sort of to end off, do you have any pieces of advice, recommendations, resources, honestly, just anything for young students who are sort of on the fence or like aspiring to either study math, like politics, poli-sci, like honestly anything in the future?
So I can get sort of more general and more specific advice. Let me start with the specific. So if this kind of thing, social science, politics, democracy, intersecting with math sounds good to anyone, then you should Google the institute that I run, called Institute for Math and Democracy. And you can just poke around the website and see what things are possible, right? So there's lots of stuff that we do with the research, education, outreach on all things math and democracy. We organize conferences, we run research projects, we have a huge network of people that has, students, professors, activists, politicians, all kinds of people who care about quantitative political literacy. So that's a good springboard for seeing or a landing place to see what's possible in this space, right? And more general advice is that there's a lot of exciting things happening in mathematics and applications of mathematics. I alluded to this earlier when I talked about, computational social sciences, etc. So as a high schooler, you don't necessarily see this, right? You're moving through a sequence of classes that, it's been like that for decades. And, trying to get to calculus. If you're really lucky, you get to multi-oral calculus or something like that, right? But there's this kind of preordained sequence that at times feels a little forced and boring, and you're like doing problems, and what's the point of this, etc. So if you have a really good teacher, they will tell you about why these things are useful, where they're applied. But it's hard to really it's hard to see the forest for the trees. It takes a while to get to the level of mathematics where you can really see the big picture, where you can see how useful it is and where it's used. And that typically happens in college. You start taking some, because you have freedom in college. You say, okay, I'm going to major in math. Sure, you have to take some calculus, linear algebra, whatever standard classes. But after that, like the world opens up. Suddenly you have like 40 classes you can take. And you fulfill the prerequisites, and you can just like this world opens up of pure math, if that's your, that's your poison, or applied math, if that's what you like. And that's where we teach cutting edge stuff, right? At these upper level undergraduate classes, you get to see what's happening right now in the world. So, for example, I'm teaching a topology, which is my field. So, in addition to teaching math and politics, I teach a topology class. And we're going to talk about, so it starts with a topic that's 120 years old, like the birth of topology, Henri Poincaré, who invented, so this is 1905 or something. So you're like, oh my God, like starting in 1905, this is going to be boring. But then very quickly, you're like, I start talking about machine learning, quantum computing, signal processing, networks, all these things that are like cutting edge of applications right now. So this is the kind of stuff you hear about when you get to college, but it takes all. So the message is try to persist, just get through that high school curriculum, get to college, and then this amazing world of applications of math will open up to you.
Okay, thank you so much for coming to this call today and sharing your experience. It was absolutely phenomenal. Thank you.
Awesome. Thank you. Great to be here.